Well, hello students, this is Mrs. Hanson. We're getting ready to begin a next new journey in organic chemistry, Chapter 10, Radical Reactions. And I have listed here the table of contents, the sections in our chapter, and just kind of color-coded how I'd like to approach this. I'd like to introduce radicals, talk about the 6 general patterns in radical mechanisms, then look at a very specific chlorination of methane as an example of those patterns, and then talk about thermodynamic considerations in this particular lesson. So I'll call this Lesson 1. Lesson 1 will cover these first 4 sections. In the next video lesson, I'm going to talk about Section 5, Selectivity of Halogenation, and the stereochemistry of halogenation. And specifically, we'll look at chlorination and bromination. And then talk about allylic bromination specifically. And I'm going to jump down to this 10th section, Radical Addition of HBr. Really kind of an opportunity to revisit the alkene chapter. When we take a double bond and sitting on an arrow, we see a boron-based compound and a peroxide solvent, and we get an anti-Markovnikov addition. We'll just look at that mechanism more in detail. There's no new chemistry there, but it's more just explanation about a previous mechanism as a radical mechanism of why it adds to the end of the chain instead of to the most substituted. And what I have in red then is what I'm saying are assigned reading sections. 8, 9, and 11, respectively, will be from your own reading and not part of the formal lecture. So with that, let's go ahead and begin looking at our first section called radicals. And in this section, we get an opportunity to just define and get a good feel of what a radical is in comparison to an anion or a cation from ionic additions. So we learned when we first met each other in this course that we can form either a heterolytic bond cleavage and a homolytic bond cleavage. Now let's remember that this is a single covalent bond, which means it's a shared pair of electrons. In a heterolytic bond cleavage, hetero, these electrons involved in the single bond are going to be taken by one of the elements, one of those atoms in the single bond, leaving the other without any. And just to kind of emphasize, both electrons ended up on element Y. With the gain of an electron, it carries a negative charge, and we know that to be an anion, a negative ion. And over here, we can see that the element X involved in this single bond has no electrons. Therefore, it is known as a cation, a positive ion. Notice that I'm using a double-headed arrow. Each tip of the arrow you can think of as carrying an electron with. So when 2 electrons are moved, we use a double-barbed arrow. Let's compare this now to what's happening in this new chapter called homolytic bond cleavage. Again, I'm going to go to a color-coded system, a shared pair of electrons in a single bond. When this bond breaks, which is what cleavage means, you're cleaving the bond, separating or breaking it, 1 electron goes with element X and 1 electron goes to element Y. Now notice the single barbed arrow. This is commonly called a fish hook arrow. And just keep in mind that it only has a place to carry 1 electron with it. So a fish hook arrow is used to move 1 electron, where we have a double barbed arrow to move 2 electrons. Element X and element Y ended with an electron, a lone unpaired electron. Now let's emphasize that these are not ions. They do not have charges. They're not positive or negative cations or anions as we saw with a heterolytic bond cleavage. Instead, we now refer to these as radicals. A lone unpaired electron on element X and Y. So we can see that the bond is broken in 2 different ways. Heterolytic. Heterolytic means both electrons go in the same direction. or a homolytic bond cleavage in which the electrons split up and one goes in each direction. These free radicals form in a homolytic bond cleavage. The shared pair of electrons are split. One goes to the first element, the second to the other element. These are not ions. They are not charged. Rather, they are known as radicals. And what makes a radical is having an unpaired electron. So one lone electron is another way to say that same thing. And again, I'm emphasizing in this section how we use a double barbed arrow to show 2 electrons. Notice there's a position to carry 2 electrons, one on each side of that barbed head. And over here with a fish hook, there's only an arrowhead to move just 1 electron. So a radical forms through a homolytic bond cleavage. In order to understand the structure and geometry of a radical, let's quickly review the carbo-cation and carbo-anion hybridization. So here we have a cation. Now the cation is a positively charged 3 bonded. So instead of the normal 4 bonds, it only has 3 bonds. And therefore, you can see this completely empty orbital. The sp2 hybridization is trigonal planar. And this means that we can have an attack from the top or the bottom, having retention or inversion of configuration. Based on the fact that we have this empty orbital, this flat planar structure, we can have an attack on the top or bottom. And here, of course, we have an sp3 hybridized anion. Notice the negative ion has electrons filling this orbital. It's not empty, it's full. So all 4 valence sp3, all 4 of those bonds are present. Electron domains are present, giving us an sp3 tetrahedral shape. So if a radical is somewhere in between, it's not an empty bond, it doesn't have 2 electrons in it, it has just a single electron. So what does it look like? Well, again, looking at this, it has 1 electron. So it's kind of, you would think it's between a trigonal planar or a rapidly inverting trigonal bipyramidal. But what happens really just based on observation is we've concluded it must behave more than sp2 hybridized, more so than an sp3. And the reason we can say that is the mechanisms, these reactions that we're going to study, show both configurations of a chiral center. So not only will we have a top side attack, we also have a bottom side attack, and you'll have a racemic mixture of any chiral center. So if it were indeed sp3, you would think that it would only have the ability to do a top or a bottom, having 100% inversion or 100% retention. But the opposite is what is observed. Based on observation, we can say that the carbo-cation configuration of sp2 is the same configuration as the radical itself. So that means everything we studied earlier about stability of a carbo-cation is going to follow the same rules for the radicals. The stability for radicals follows that same trend exhibited by carbocations. So in the tertiary radicals are more stable than the secondary radicals, which in turn are more stable than the primary. And let's put that into a visual. So radicals we know are neutral. They are not ions, but they're still electron deficient. They are not a complete octet, but they follow the same trend for stability as the sp2 carbocation, which means the most stable configuration places the lone electron on a carbon that is the most substituted carbon. So the least stable is placing a lone electron on a carbon that has no carbon attached, a methyl. A primary has the carbon that's attached to this lone electron attached to just one carbon. If the carbon that has the lone electron is attached to two other carbons, we call it secondary, and a tertiary, the most stable of all, just as it would be predicted for a carbocation. And just to verify this, we know that bond strength is inversely proportional to the carbon radical stability. In other words, the general trend is right here. The weaker the bond, the greater the stability. So if we compare bond dissociation energies, BDE, bond dissociation energy, how much energy does it take to break a bond? Well, here the carbon to hydrogen in a methyl takes 435 kJs per mole. A little bit less in a primary, a little bit less in a secondary. And the lowest amount of energy needed to break this bond is found in a tertiary, which would translate to saying the bond that breaks this bond here then becomes the position of the radical. This is the most stable configuration. So the weaker the bond, the greater the stability. The easier it is to break a tertiary bond than the methyl bond. It takes less energy to do that. And so we can just think about that a little bit and practice some of like homework questions. This is taken from 10.1, a conceptual checkpoint. So you'll see this on your homework. It just simply asks us to rank the following radicals in order of stability. And I'd encourage you to pause the video and think this out. And then when ready, come back and let's compare. So in your notes at this point, you've drawn out the three structures for letter A. You've drawn out the three structures for letter B. Draw them onto your paper. And then tell yourself, what type of structures do we have? For instance, this carbon attached to the lone electron is attached to just one other carbon. We called that primary. This carbon with the lone electron is attached to three other carbons. Therefore, we know it to be a tertiary. And here we can see that this is a secondary. We understand that the most stable arrangement is the easiest bond to break. And that bond that would be broken would come from the CH bond located in this particular tertiary position. So this would be the most stable, whereas the primary would be the least stable configuration. And this skill goes on to do the same thing here. You have a secondary position, tertiary position, and a primary position. Knowing that the least stable has the carbon with the lone electron attached to the fewest number of carbon. And the most stable configuration would have the lone electron attached to a carbon that's attached to the most carbon. And we'll see quite a few of those type of questions as we proceed through the chapter. So radicals, like carbocations, are also stabilized by resonance. And this is because they can delocalize the bond. We're going to practice delocalization of resonance using the fishhook arrows, and they're used to present all the possible resonance forms. Now I'm going to introduce a vocabulary word that I want you to know is very important, the allylic position. These two carbons are involved in a double bond. The allylic position is one carbon adjacent to a double bond. If you see a lone electron on a carbon that's next door to a double bond, this has the ability to be resonance stabilized. Let's take a look at how that happens using fishhook arrows. If I just redraw this, I can emphasize just by using some colors. Let's say that these two electrons are blue, and I'm going to make this radical, this lone electron, red, just so we can see where they end. Now, a resonance stabled electron says this electron that is a lone will come to the center, as will one of the two electrons in the pi bond. Now notice I have to start the arrow on the bond and bring it to the center. What we've just formed is a pi bond made of one that was originally red and the other that was originally blue. We need one more arrow, and that's to take this electron and make it become the radical lone electron at the end of the carbon chain. We used 3 fishhook arrows to draw the resonance structure, that's plural, of the allylic position. When the lone electron is next to a pi bond, it is resonance stabilized. Not only can we look at allylic resonance stabilized, we can also expand this into a discussion of a benzylic radical. Remember, the more double bonds in the allylic position, the more delocalized, it means the more structures we can draw over more and more carbons. So let's take a peek at a benzylic radical. I'm going to redraw with you just so we can talk through these pictures, and I encourage you to draw these on your paper as well. So here we have a benzene ring with a methyl and a radical at the end of the chain. Now remember, allylic means that this lone electron right here is next to a pi bond, which is right here. Let's color code these electrons just so we can see. We'll kind of make that one green and the two that are in the pi bond red. So the first fishhook moves this lone electron, one arrow there, to begin the next bond. This is going to become a pi bond. The red electron, remember, originated from the pi bond and bring it over so that these two electrons become a new bond. So right now we have a pi bond made of one green and one red electron. Now we still have this lone electron over here, and what we do, start at the pi bond and just deliver it to the carbon next door to the allylic position here, so it ends up here, and now there's the rest of those bonds. So that is our first structure. But notice again, we have another allylic position. Here this lone electron is adjacent to, in the allylic position, that double bond. So we repeat the process. This electron with a fishhook arrow and this electron with a fishhook arrow will go on to form a next double bond. This electron here goes to the allylic position with the fishhook, and now there's our next resonance structure. And that pattern will continue where this electron is now adjacent to this pi bond, and this pi bond will break apart and form yet a next structure. And by the time you're done moving all of those structures around, we ended up with 1, 2, 3, 4 unique structures, and this is back to the original picture. So the key here is finding a lone electron adjacent to a double bond. That's the criteria to be resonance stabilized, and use 3 fishhook arrows to create the next resonance structure. And just to remind ourselves that this is because the weakest bond is always the most stable configuration. Now on the previous slide I mentioned that tertiary was very stable. But now I'm saying that even better is a resonance stabilized structure, such as the allylic carbon. It takes less energy to break that bond. And even more stable than the allylic is the benzylic position. It takes less energy to break that bond. The weakest bond forms the most stable radical. It takes less energy to break apart this carbon to hydrogen bond. Therefore, when we create a radical, which would just simply look like, and I'll just make a circle there for the alternating bonds, that carbon ends up with a lone pair of electron. When this bond is broken, homolytic cleavage. Well, let's practice that. Kind of going through step by step, practice the skill of drawing all possible resonance structures given any type of situation. So here's just kind of redraw this with me on your paper. We have a cyclohexene, a lone electron at the top carbon, and a alkene branch coming off. Looks like this. So again, step one is find any type of scenario where you see a lone electron next to, in the allylic position to the double bond. And yes, indeed, this meets that criteria. We have a lone electron in the allylic position. Remember, these are the two carbons that are in the double bond. The allylic position is adjacent to that, one position over from the two carbons in the bond. That's the allylic carbon. And that's the criteria to have resonance. And so what we end up doing, we're going to take the lone electron with a fishhook arrow and bring it in. We'll break apart the original pi bond and bring one in. And what forms is a new pi bond. This electron here needs to come out, and it needs to go onto that last carbon. Let me just get that written there, and it ends up here. So 3 fishhook arrows were used. Arrow number 1, take the lone electron and begin the formation of the pi bond. So arrow 1, let me make that a little bit neater. A fishhook, bringing it in. Arrow 2, break apart the pi bond and bring 1 electron to form this bond here, leaving the lone electron on the allylic position of the new pi bond. Now something interesting happens here as well. I have a second pi bond that meets the criteria of an allylic position. Here's a lone electron in the allylic position of this double bond. So we can draw yet another resonance stabilized structure. We're going to take this lone electron with a fishhook arrow and bring it in to start the formation of the pi bond. This set of electrons gets cut in half, and we end up with a new pi bond in this position and the lone electron at the end. So there are 3 unique resonance structures for this particular example. And you're going to see all 3 of these, kind of this structure over and over again for homework questions. So just as a sample, this is a homework question in your Wally. It's going to say, draw resonance structures for each of the following radicals. So again, find the allylic pi bonds for resonance. That means if you see a double bond, look to see in the allylic position, that's 1 carbon adjacent, if you see the radical, the lone electron. And if so, it takes 3 fishhook arrows to create the resonance structure. The first, the lone electron, forms the beginning of a pi bond. One of these 2 electrons breaks apart. The second of those electrons ends up as the lone electron. And then just draw what you end up with. There's the cyclopentene. That didn't come out very well. That's a little better. And here is that original methyl group. we moved the pi bond to this position, and now the lone electron is in the allylic position to the new pi bond formed. And this can go back and forth. And that's an easy enough practice. I can kind of share with you the first position and the second position is just looking at the allylic pi bond. One thing to note down here, when this radical gets moved, and so I'm looking at this example on the next screen, this example creates a pi bond in this group here, but it is not in the allylic position to the lone electron. So therefore, the second pi bond does not participate in that letter D. There are only two unique structures there. So in this section, we've seen that the allylic and benzylic radicals are stabilized by resonance. And one point of emphasis, if these are the two carbons that are involved in the double bond, the allylic positions are one carbon away. They're not the carbons that are in the bonds, that's vinylic. Instead, they are adjacent. And that's critical actually because the vinylic position is even less stable than a primary position. So if this two carbons are in a double bond and it has the lone electron on it, that's very, very unstable. So far that you would see in terms of stability that vinylic carbon-hydrogen bond is less stable than a primary, which is secondary, then tertiary, then allylic, then benzylic, just to kind of put them all in order. So these two are resonance stabilized. This is not resonance stabilized and therefore a very unstable configuration. So your practices really will come in the following ways, and we're just trying to give you some words so that you can recognize what you're really being asked to do when you see your homework. For instance, it says learn the skill, and it just simply asks you to identify the weakest carbon to hydrogen bond in the following. So when I see that, it's really just asking me, what is the most stable radical? Where can I place a lone electron and have it stabilize the greatest? So where is the most stable radical? Well, a beginning learner might be tempted to think this carbon is the most stable configuration because it is the most substituted. And I emphasize that that's not correct because this carbon has no hydrogen on it. And therefore, it doesn't meet the criteria of meeting the CH bond being the weakest. So that is not a correct answer. I do recognize that there's a double bond, and right here I have an allylic position. So as you talk through the strategy in your own head, just try to start visualizing where are all the CH bonds and what type of radical would it make. If I removed a CH bond from the terminal ends, we create primary radicals. If I were to create a radical here, this is pretty good. It's a tertiary, which is pretty stable, but not as stable as the allylic position. And don't be fooled that the vinylic, it's not the two carbons in the bond. It must be one position over to be resonance stabilized. So of all of those positions, we understand the best position would be this carbon that has an allylic position to the double bond. That would give us the most stable radical. And that's all that question really was asking. And so again, you'll see many questions in these first few sections kind of asking the same thing, but with different words. Identify the weakest CH bond. Ask yourself, where is the most stable radical? Where could that be formed? Think about all the different positions and where the lone electron could be stabilized through resonance. Here is a carbon in the allylic position. Here is a carbon in the allylic position, but it is only this carbon that has a CH bond. This carbon already has 4 bonds, all to carbon, so he's kind of off the plate. And so you can see, as I visualize all of those hydrogens, you want to select this guy, and the reason is it has the ability to be stabilized through resonance. And so just to kind of think that through, you'd have this radical, which is a tertiary radical, and the allylic position. Boy, is he all sound. He's looking pretty good. Let's talk through about the second section of our chapter, patterns in radical mechanisms. We will see that there are 6 general patterns that we will need to memorize as we go through this section. So recognition of the 6 mechanisms will be critical in this section. It just shares with us that, like ionic mechanisms, radical mechanisms follow specific patterns, but these patterns are very different mechanisms than ionic reactions. So for example, here we know that a carbocation in a secondary position could undergo a hydride shift or even a methyl shift to create a rearrangement, and a tertiary carbocation would form. That's because we have sp2 hybridization. There is an empty orbital available, oops, I spelled that wrong, an empty orbital available for something to come fill it in. So I'm trying to write orbital. Keep in mind right here, this is an empty orbital. So something like a hydrogen or a methyl could come and shift, and you could create then a tertiary carbocation by doing a hydride shift. But their criteria there is saying that this hydride shift occurred because this was empty, but it's not empty here. There's an electron there. So therefore, seeing that it has a placeholder already, it will not undergo rearrangement. So keeping in mind there's distinct differences, that being one of them, between the mechanisms that we've been studying in the previous chapters, where we had heterolytic bond cleavage, and now we'll look at 6 key arrow pushing patterns for radical mechanisms. And let's explore these one at a time. In the first mechanism, this one is known as homolytic cleavage. Let me just use a little color coding. Here is a single covalent bond. It's a shared pair of electrons. That bond cleaves. This is like our very first, opening to the chapter. We use a fish hook arrow, and one electron goes in either direction, and we create 2 radicals. Emphasize that this must occur with some sort of initiation. The heat, or HV, is energy from thermodynamics. Energy is equal to Planck's constant times the frequency. So HV is how you'll see energy written there. So you need a little zap of energy. Homolytic bond cleavage. You break the bond, the electrons go in either direction. A second general pattern is called addition, and we add across a pi bond. So here we have a radical, a lone electron, and here we have a pi bond. Remember, that is a shared pair of electrons. One of these electrons from the pi bond will form a new bond from the X radical. So thinking that through, let's color code. If this is red, it's now this electron here. And if this is blue, that's this electron here. And finally, if we make this purple, this ends up to be the purple at the end of the carbon chain as a radical. The third general pattern is called a hydrogen abstraction. It's not the same as a proton transfer because the proton would not have any electrons come with it. This is a heterolytic bond cleavage, meaning that we're going to separate them out. Homolytic bond cleavage, we're going to separate the 2 electrons. So a shared pair of electrons. And what happens here, let's make this one green. And so the new bond that forms has 1 green and 1 purple, and that new radical that formed is the other purple electron. I'm going to just come back and emphasize, you notice homolytic has 2 fishhook arrows. I only needed 2 arrows to break that bond. The addition reaction required 3 fishhook arrows. The hydrogen abstraction also required 3 fishhook arrows. We're going to carry that theme through the rest of those. The fourth general pattern, very similar to hydrogen abstraction, instead of taking off a hydrogen, we're just removing a halogen. So I think 3 and 4 are very similar, just taking a hydrogen or a halogen. So if this is a diatomic molecule, such as chlorine, Cl2, or bromine, Br2, and we have a radical carbon chain, R with a lone electron. Notice that we use 3 fishhook arrows, and if we color code, the original electron on the R radical is now here as part of this sigma bond. The purple electrons in the original shared pair have now separated, and we have left a halogen radical and a new halogenated alkyl. Number 5, the 5th general pattern, is known as elimination. In the elimination process, it is exactly the reverse of addition. So the radical on the alpha carbon is pushed toward the beta carbon to eliminate the atom or group that's being pushed out. Notice again, we have 3 fishhook arrows. So a moment ago, we added the X onto the chain. Here, we're eliminating the X off the chain. So here is the bond that breaks. The radical X is reformed, and the original pi bond is restored. Elimination puts the pi bond back together. And the last of the 6 general patterns is known as coupling. This requires 2 fishhook arrows. This is the opposite of cleavage. A radical with its 1 electron will pair up with a radical with its 1 electron and form a single covalent bond known as coupling. So here we've seen the 6 general patterns. I'd like to maybe put these together a little bit and have us kind of think about what's forward and what's reverse and make some connections. So although we saw that there were 6 general patterns, we really can understand that there's 3 processes. For instance, in a homolytic cleavage, a shared pair of electrons are cut in half when the bond breaks. However, if I put the bond back together, and I do so by just putting those single barbed arrows together there, we can put the bond and restore it in coupling. Break it, put it back together is cleavage, then coupling. We also mentioned that addition and elimination were opposites of each other. If I have a pi bond and I want to form a longer chain, I want to add on a halogen to a pi bond, we can do so with 2, and then this guy comes out for a total of 3 fishhook arrows. And then of course the opposite of that is restoring the pi bond through the process of elimination. And then the last group is hydrogen abstraction. In other words, if I have a hydrogen attached to a carbon chain and I want to abstract the hydrogen, I can do so and add the hydrogen onto the halogen and leave the radical as the carbon. But the reverse order really is not opposite. It's just going the opposite. I mean, it's the same process. The radical can either be the carbon chain or the radical can be the halogen, and it's the same mechanism either way. So they're not opposites, but you can see that in this hydrogen, you can substitute the word halogen, and it's the same process. So here we have all 6 of those, and just as a reminder of how many fishhook arrows it takes. In a homolytic cleavage, a bond breaks. Each electron goes its separate ways. We have 2 arrows. In addition to the pi bond, we have 3 fishhook arrows, and we've lengthened from 2 pi to what we have here is the pi bond into 2 sigmas, adding on. Here in abstraction, this bond breaks, and we form a new bond, leaving the radical on the carbon chain. That can happen as a halogen or a hydrogen. If the halogen bond breaks, same process. Elimination restores the pi bond, and coupling restores the single bond sigma. Let's practice. Let's draw all the appropriate fishhook arrows for the following radical process. So let's kind of get an idea. We have a cyclohexane, and it has a methyl group coming off and a lone electron, making it a tertiary radical. It's stable. And then think about the bromine as being a single bond in that molecular bromine molecule. Br, single bond, Br. And to kind of emphasize that, we can color code and make those electrons a different color. Now on the other side, what we've added on is a bromine to that cyclic structure, and the radical has become the halogen. When you've got that written down, let's kind of go through the step-by-step process and just think out loud of strategy. Strategy 1, let's determine what type of process this is taking place. So you see a radical is reacting with molecular bromine and resulting in a transfer of a bromine atom. Write down on your paper what you believe out of the 6 mechanisms, which one was that? Well, if you said halogen abstraction, that's exactly right. The halogen abstraction, this bromine is going to add on, be abstracted to add on to the carbon chain at the position of the lone electron. That's the site of addition, is at the lone radical electron. And now that you know that, we have to determine how many fishhooks will actually be necessary. Remember, there were only two situations. It was the coupling or the bond cleavage that required 2. Every other one involved 3. So we know that we'll need 3 fishhooks by the time we're done drawing this mechanism. And we also wanted to encourage you to talk through about where is the bond being broken and where is the new bond being formed. And as we keep track of that bond broken and bond formed, that helps us figure out where the arrows are going to be placed. So for instance, let's just color code those 2 electrons, and I'll place this electron as green. This electron, the radical lone electron, is reaching out to form a new bond. The bond here is reaching out, forming a new bond. So the first 2 fishhook arrows are forming a new sigma bond, a single bond, onto the cyclic structure. The original bond still has this electron, and we just need to show that collapsing onto the bromide. So there are your 3 barbed arrows. So we formed a new bond. This was originally green, this was originally blue, and that was the other blue electron. Notice this is called a radical, not an anion. It is not the same as bromide, who would look like this. That's an anion. These are not charged. Radicals are not, they have no formal charge on them. So just to kind of emphasize that. And really that's the pattern as we kind of go through these particular examples. You're just asked over and over to fill in the mechanism. You know, what's going on here? Envision all the bonds, and how do I turn the left side into the right side? So if I have a radical, this is a tertiary position, so it's very stabilized. I can see that the hydrogen is being abstracted and the new radical is left on the halogen, the bromine. So we would require 3 fish hooks to complete this mechanism. The first takes the lone electron and reaches out to form a single bond. Here is the shared pair of electrons in the HBr. The first is reaching out to form a bond. Those are both single head or fish hook arrows. And the last one just simply collapses that other electron onto the bromine. And we've identified all 3 fish hook arrows for that mechanism. And again, you can see the hydrogen abstraction requires 3 fish hooks. The 3 fish hooks have to show where the bonds are being broken, where the bonds are being formed, and just make sure you draw in the fish hook arrows. And I always like to color code so you can see where they started and where they ended. Multiple practices available for that skill in your homework. This might be a good place to pause. I know I promised all 4 sections, but I think I'll do 2 and 2 just to give myself a little break from talking. So I'm going to conclude the video here for sections 1 and 2. I'll do a next video of section 3 and 4 and a third video for section 5, 6, and 10. Come on back when ready.